Hi there, and welcome to 3.6 solubility product. Okay, as you'll see in your notes, your first thing to do there was to define solubility. This is something you should all be aware of. But solubility is the maximum amount of solute that can be dissolved in a particular volume of solvent at a particular temperature. Okay, number 2 here, we're looking at the solubility of lead 2 chloride at a certain temperature is 4.4 grams per liter. But remember, anytime we're dealing with our concentrations, whether we're talking solubility or equilibrium or anything like that, we are talking about molarity. So we're going to have to switch that out, which is what we're going to get to in part B of this first one here. But if we're looking at part A, we want to write out the balanced equation. So for part 2A, we have our PbCl2 solid. Where did I reach there? I need to turn that back on. Is in equilibrium with our Pb2 plus aqueous and our 2Cl minus aqueous. Okay, hopefully you can read all that. Let's just rewrite this part here so you can see that a little bit better. 2Cl minus aqueous. Okay. So there's our equation. Make sure we're realizing that we have this equilibrium equation, okay, for the solubility. We've got whatever solid we're dealing with is in equilibrium with our ions. Okay, remembering that we do need just a couple crystals of that solid to be that solid or that equilibrium state. Okay. Question B here is we want to take this 4.4 grams per liter, okay, and we want to convert that to moles per liter. So what we're going to have to do is we're going to have to multiply this by the inverse of our molar mass, and for, sorry, I'm blocking your view here, for lead chloride, that is 278.2 grams. Okay, so I'll just leave that up to you guys to double check that using your data sheets, the back of the textbook. Okay. Keep in mind, if any of you don't have your textbook, please contact me. I know there's a couple people that didn't. You are possibly able to email the school. I believe that was sent out from the school to all students. You may be able to go in and pick up your textbooks as long as you email or call ahead to do so. However, like I said, if you don't have those, send me a message. I'll see what I can do for you. All right. So back to this calculation. Now we're just at our 4.4 divided by 278.2, and this equals 0.0158 moles per liter. But we don't want to forget our sig figs, and since we had 4.4, we are going to say then that this is approximately 1.6 times 10 to the negative 2 molar. Doesn't quite look right here. Let's 1.6 times 10 to the negative 2. Okay, hopefully you can see that okay. And then part C. What are the different ion concentrations? Well, for that, we're just going to look up to here and see that this here was our solubility, or the for the PbCl2. And so we've got a 1-to-1 ratio with our lead. So pop this up here a little bit. We have our Pb2 plus equals that concentration of the PbCl2, which equals 1.6 times 10 to the negative 2 molar. Okay, so you guys can see that there. And then our Cl minus concentration is twice that lead chloride concentration. So then we have 3.2 times 10 to the negative 2 molar. Okay, everything there should have been in review. Hopefully you're all okay with that. See you in a second. All right, just cleaned off my whiteboard there to continue this on. Now, if you're following along in the notes, you'll see that I've talked about, since solubility is a form of equilibrium, and we had our equilibrium constant, our KEQ, which is our concentration of our products over reactants. We have a very similar process with our new constant we're going to deal with, our solubility constant, our KSP. Okay? And now, this again is also going to be the concentration of our products divided by the concentration of our reactants. But now I had that question in there just before this that says, what items do we not include in our equilibrium expressions? Well, we ignore pure liquids, so when we only have one liquid in the entire reaction, and also our solids, right? We don't have a concentration for our solids because it is just that, it's a solid. So if we're not looking at our solids, remember, we had in that reaction, we had our lead chloride solid in equilibrium with our lead ions and our chloride ions. So since we're talking about our reactants here, we can ignore our reactants because that is just our solid. And that now makes our KSP, for this example, just our concentration of our lead multiplied by the concentration of our chlorine. And just like we did in the last one, our coefficient for our balanced equation is also our exponent on that chloride ion. Okay, so our KSP then, a little bit easier than our KEQ. We don't really have to worry about the reactants so much. We're just looking at the concentration of those ions raised to the power of the coefficients in that balanced equation. Okay, so if we look here from our previous part, we had our lead concentration was 1.6 times 10 to the negative 2. Our chloride concentration was 3.2 times 10 to the negative 2, right? And then we have to square that. So just entering these into our calculator, we get a value of 1.6384 times 10 to the negative 5. But keeping in mind that we have to pay attention to our sig figs, we are left with 1.6 times 10 to the negative 5. Okay. All right. Now, we got a couple definitions there on the notes. We have, oh, that's not going to work here. Hold on 1 second. Molar solubility and the solubility product, right? So that product is just our KSP is our solubility product. It is going to be that concentration of our ions in solution raised to the power of their coefficients. And just like our KEQ, our KSP has, so let's put a star here, no units. Right, because every time we have this KSP, those units could change. So we just ignore units for our KSP, remembering that our concentrations must always be in molarity or moles per liter. Okay, we're back again. Sorry for all the pausing. I've got a very small whiteboard. I'm trying to make sure I write it big enough that you can see them all here. We're switching over to that 3.6 example sheet. Okay, and remember I don't have room to write all these questions, so I've given you those typed out just to help you along. Okay, so remember here at the top it says, for each type of question, be sure to show balanced equations and your KSP equation. And remember, just like I said prior to this, no units for the KSP, and all of our concentrations must be in moles per liter. All right, example 1. A solution contains 6.5 times 10 to the negative 5 molar CrO4, negative 2, and 1.03 times 10 to the negative 4 molar Ag plus to form equilibrium with that silver chromate. What is the KSP? Okay, so first up we're going to take our Ag2CrO4 solid, and that is in equilibrium with 2Ag plus and our CrO4 2 minus. Pardon me for a second, I'm just going to get those wires behind here. All right. And now both of these, since they are ions, lets us know that they are aqueous. And that gives us then our KSP is equal to that concentration of the silver multiplied by that CrO4 2 minus. But we've got that coefficient of 2 in front of that silver, so we need to square that silver concentration. So we plug these values in. Let's see, we had said for our silver we have a 6.5. Nope, sorry, that was our chromate. Let's go back here. 1.3 times 10 to the negative 4 squared. Okay, and we're going to multiply that by our chromate, which was the 6.5 times 10 to the negative 5. Okay, and we don't need to square that. And where to put my calculator? Let's just do this up real quick. 1.3 times 10 to the negative 4 all squared. Sorry guys, I'll make sure I don't do this next time. Times 6.5 times 10 to the negative 5. And this gives us a value of 1.10 times 10 to the negative 12. And again, no units in there. Okay, here we are with your second example. I just went ahead and wrote some of this stuff out to shorten the length of this video. So we have a saturated solution of magnesium hydroxide is made by dissolving 5.5 times 10 to the 5 moles in 500 mils of solution. Calculate the KSP. Right, so we started off with our balanced equation. We've got the solid magnesium hydroxide, breaks down to our magnesium and 2 hydroxide ions. And then our KSP, products over reactants. We have the concentration of magnesium times the concentration of hydroxide squared because of that coefficient, and ignoring the reactants because we don't include that solid magnesium hydroxide. Now, if we're looking at the concentration of that magnesium hydroxide, we have the 5.5 times 10 to the negative 5 moles divided by the half liter that we dissolve that in. And so that gives us a 1.1 times 10 to the negative 4 molar solution. Okay, now since we have the 1-to-1 with our magnesium, we can look at our KSP is going to be that 1.1 times 10 to the negative 4. Okay, that was the concentration of our magnesium. Our hydroxide is double that, so we would have a 2.2 times 10 to the negative 4. And then we have to square that. And so when we plug this in and consider sig figs, we get a KSP of 5.3 times 10 to the negative 12. Okay, this last example is a little bit more complicated, but really there is only a couple different ways that we can do these problems where we're given the concentrations and want to find the KSP, or we're given the KSP and need to figure out the concentrations. And that is essentially what this problem is going to look like. So there's very little information in this problem, but if we take a look at our data table at the back of the book, we can find that this strontium fluoride has a KSP value listed for us of 4.3 times 10 to the negative 9. Okay, now again, that doesn't really seem like enough information, but we want to go back here and we're trying to figure out what this strontium concentration is. So let's give that the value of X. And since we don't know what our fluoride concentration is either, we can just compare that molar ratios and give that a 2x value for the concentration. So now we can take a look here at our KSP being our X multiplied by our 2x, right, the concentration of the strontium and the concentration of the fluoride. But we've got to square this. But now that is our KSP equation, so this will be equal to 4.3 times 10 to the negative 9. If we square this 2x, we get a 4x squared. Multiplied by that x, we get a 4x cubed equal to 4.3 times 10 to the negative 9. Okay, so just doing a little bit of algebra here, I'm going to divide both sides by 4, and then once I take this side, which will be about just less than 1.0 times 10 to the negative 9, okay, I'm going to take that value, I'm going to cube root it, and I'm going to get to the value of x equal to 1.0 times 10 to the negative 3, and since x is representing the concentration of strontium, my units are molarity. All right, I'm starting to get a little bit of a glare here as the sun's starting to come out a little bit, but hopefully you can still see that okay. So we're looking at this example 3 follow-up, and that's saying what mass of strontium fluoride will dissolve in 500 mils of water. So, still got that same equation. We realize that this X represented the concentration of strontium, so that would also be the same value for the strontium fluoride because it's the 1-to-1 ratio for that compound. And I have although we said X was 1.0, I carried that extra sig fig over to do this calculation. So, what we're going to look at here is we need to figure out what mass. All right, so I'm going to take my 1.02 times 10 to the negative 3 moles per liter. I'm going to multiply that by the 0.500 liters that we're looking at. Right, we said 500 mils, so 0.5 liters. Now, those liters would cancel out. Right, we can cancel out those liters. We're now in moles, but it didn't want to know moles, it wanted mass. So we then have to multiply this by our molar mass of the strontium fluoride, which is 125.6 grams per mole. Those moles cancel out, and we are now in grams of strontium fluoride that can be dissolved in this solution. And multiplying everything out here, we get to a value of 6.4 times 10 to the negative 2 grams of strontium fluoride that can be dissolved in a half a liter of water. Okay, folks, moving on to section 3.7. This is the predicting to precipitate, so hopefully you've read those notes. Okay, we're going to be using these solubility charts to understand which compound we're going to get as a solid here. So in this equation, this example that we're looking at, we've got a aqueous sodium carbonate and an aqueous magnesium chloride. When they combine, we're going to get two sodium chlorides, which we should all know is soluble. And that means that we're going to get a solid magnesium carbonate formed out of this. Magnesium carbonate being the one that has the low solubility. So if we're looking at just that one compound, everything else is going to stay aqueous. We can say that we've got the magnesium carbonate solid is in equilibrium with the magnesium and carbonate ions. We can also look at the KSP for here as that magnesium concentration times the carbonate concentration. And from the data table at the back of the book, we get 6.8 times 10 to the negative 6 as our KSP value. We then want to use this KSP value, which would be what we need to get a saturated solution. And we're going to compare that with the given concentrations of those ions from the sodium carbonate and magnesium chloride solutions. Now we want to be careful here. We have to perform dilution calculations on those in order to find their calculation or concentrations. Once we have those, we're going to figure out our trial KSP, our value Q, which is telling us what we actually have. And then we compare that to the KSP to predict whether or not we get a precipitate from this low soluble solution. All right, as I said, we need to figure out our diluted concentrations here. So I'm taking the sodium carbonate. We're told that we have a 0.02 molar solution, and we had 23 mils that we were mixing with 12 mils of the other. So that gives us our dilution calculation here being the original concentration multiplied by the volume of that divided by the new total volume. You'll notice that I haven't changed any units here because milliliters divided by milliliters cancels out and we're still in that molarity. If you're having difficulty with your dilution calculations, make sure you go back and review those. But taking my concentration of sodium carbonate, that is a 1-to-1 ratio with the carbonate ions, so I don't have to worry with any conversions in there. I just have to dilute that and I get this value of 0.013. Performing similar calculations for the magnesium chloride, it's again 1-to-1 with the magnesium ions, so I can just dilute the magnesium chloride solution to the total volume and get a 0.0034 molarity. Okay, I just rearranged a few things on here. So we have our actual KSP sitting at the top, right? We've got that magnesium ions times the carbonate ions, and just taking that value from the data table, 6.8 times 10 to the negative 6. Now, that's what we need to form an equilibrium situation, okay, or to form that solid. Now, if we are looking down here, our calculated, what we have is 0.013 molar carbonate and our 0.0034 molar in magnesium. So we're going to use those values to get our Q, our trial KSP. Just going to plug those two values in, multiply them out, and we see that we have a 4.4 times 10 to the negative 5 for our Q. And since our Q is greater, sorry here, this is a little awkward, KSP, our Q is greater than our KSP, therefore our precipitate forms. Okay, sorry, awkward writing the way it's written here, and I'll move, there you go. Okay, since our Q is greater than our KSP, a precipitate forms. Alright, welcome back. I've moved locations so the sun isn't glaring off the board for you, and we'll get to this last example. Okay, acid-base titrations, or actually any titration for that matter, is used as a method to determine the concentration, an unknown concentration by using a known solution, which we call a standard solution. And so in this situation, we're looking to try and find the concentration of salt, the sodium chloride, in the seawater by using the precipitation method of looking with silver nitrate. Okay, now although this is in the KSP section, we're not actually using the KSP calculations. We are just using our titration calculations. We are just using the theory behind solubility to figure out this indication. Now, if you read through that very lengthy example there, we start forming this white precipitate, the silver chloride. And then once all of the chloride is used up in this reaction, then we start getting that red precipitate, and that's how we know we've reached the end point. Very similar to when we're doing an acid-base titration, where we use a pH indicator, usually phenolphthalein, that changes color when we've used up all of the acid ions or the hydrogen ions in there. Okay, we'll talk more about those next week. Or sorry, next units when we talk about acids and bases. But for this one, really all we're looking at is that we had a 2.5 milliliter sample of the salt water or the seawater, so the sodium chloride solution, and that we needed 13.8 milliliters of our 0.1 molar silver nitrate solution. Now we've got a 1-to-1 ratio for this silver and chlorine to form that silver chloride solution, so we can just use that 1-to-1 ratio, makes things nice and easy for us. Now, what we're going to do here is we're going to take that 0.100 moles per liter of that silver nitrate to find and multiply that by the 0.0138 liters. Okay, you can just do that by yourselves, or that extra transmission by yourselves. And this lets us know that we needed 0.00138 moles of silver. Okay, and now since we had that 1-to-1 ratio, that means that that is also our number of moles in our chlorine in our sample. So we can then take our concentration of chlorine is going to equal that 0.00138 moles divided by the 2.5 milliliters, or our 0.00250 liters. Okay, and that gives us our concentration of chlorine in our salt sample, our saltwater sample, of 0.552 molar. Okay, those ones are, like I said, we're not using all the same calculations as we did from those previous KSPs, but we're just using those ideas to get through this. Okay, that's everything for this week's lesson. You've got that assignment on there. I've shrunk it down a little bit than what I would normally do, but there's still quite a few questions in there. Take a look at those, try to figure them out. Talk to your classmates, use your textbook or your other resources to access information that you might need. If you have any questions, post them in the thread below this video, and if they're urgent, I will get back to you right away. If they are not urgent, then we will discuss those when we meet up on Friday at 2:30 for our next chats. Thanks very much. Stay safe, be healthy.